Hey everybody, I want to show you how to do a chi-square test of a single variance. It is different than the other two tests that we have done, or excuse me, the other three, the goodness of fit and the independence and homogeneity tests, which are really kind of the same test. It's very different than that. In fact, it's not even for qualitative data at all, it's for quantitative data. So let me share up the notes and we'll start doing this. So here's the idea. Sample variance follows a chi-square distribution. Or excuse me, I should say the sampling distribution of sample variance is a chi-square distribution. So what that means, and it's this chi-square distribution, or that's how we calculate our chi-square test statistic. Yeah, so basically that's what we're going to do. So in the same way that the sample mean, the sampling distribution of the sample mean is a normal distribution, the sampling distribution of the sample variance is a chi-square distribution. So we're doing a one sample quantitative data test of variance. That's what test of single variance is. So what we're going to have is we're going to have a null hypothesis of variance is this number, and then the alternative hypothesis is going to be variance is greater or less than or not equal to that number. Yeah, so let's see how one goes. So it's a one sample test comparing a single statistic to a hypothesized number. So it's comparing sample variance to a hypothesized population variance, and we're going to test to see if that sample variance is different enough from the hypothesized population variance to make us think that the hypothesized population variance is not correct. Exactly the same way as we would with means, right? Where the null hypothesis would be the mean is this number, and then the alternative hypothesis is the mean is greater or less than or not equal to that number. And if the sample mean that we got was different enough from the hypothesized population mean, we would think that the hypothesized population mean, the null hypothesis, was not correct, and that we would go with the alternative hypothesis. Same thing, but with variance this time. And since variance follows a chi-square distribution, that's the distribution we'll be using. Your test statistic looks like this. Chi-square is n minus 1 times s squared over sigma squared, where so s is the sample variance and sigma is the hypothesized population variance. The degrees of freedom, n minus 1. So here we go. I guess before we start doing it, let me just make this point to you here. The word in English that describes standard deviation or variance is consistency. If something is more consistent, it has a smaller standard deviation or variance. If it is less consistent, it has a larger standard deviation or variance. So when you see the word consistency, or any synonym for that, none are springing to mind immediately, and we're a little worn out right now. Any synonym for those, they're referring to standard deviation or variance. Now, keep in mind, our test is about variance, but it's often given in terms of standard deviation, like I think I did in my example. So we've got this. All right, so this is kind of a long-winded thing because it's about teaching and it's about me. So of course I had a lot to say. This is actually a thing that I do when I'm giving tests. At least not so much in statistics. It's actually really hard to adjust stats tests. But in algebra classes, this is often the thing that I'll do. So in general, I'd like my exams to have a standard deviation of about 10 points and a mean of about 75. Actually, this 10 points I've adjusted it up over time. I'm usually pretty okay with 15. And a mean of about 75. So the way I can adjust this, and this is going to seem a little bit counterintuitive, but to get a smaller standard deviation on test scores, I generally need to have a larger variety of questions. Here's why. If I have on a test, like all medium difficulty questions. Like I just put every question is like, if I'm rating them on like a 1 through 5 scale of difficulty, 1 being easy and 5 being hard. If I make the entire test nothing but 3s, I will get an enormous standard deviation in results. And the reason is, if I ask a bunch of 3 questions, then anybody who can answer a 3 question, which I'm thinking of as like a C student, is going to get them all right. And anyone who can't is going to get them all wrong. And so what you get is this huge split of like a bunch of people with A's and a bunch of people with F's. And that ends up having a huge standard deviation. What you really want is to have a variety of questions so that everybody can get some of them, but people fall on the sliding scale, right? Only the best students can get the hardest questions, and but even the worst students can get the easy ones. So you want to make your easy questions really easy, and your hard questions really hard, and have kind of like only 1 or 2 of each one, and then like a gradation in the middle. So the reason I care about this, the reason I'm telling you all this, is that I can look at the standard deviation that I get on a test and use that to guess whether I made the questions too clustered around the mediums, or if I did a good job of getting enough easies and hards on there as well. So large standard deviation tends to mean that I've clumped up my question difficulty too much. I need to spread them out a bit more. So that's what I actually do when I'm looking to adjust a test, is I'll go look at the grades on the test and see like, okay, the average was 73, which is fine. And then the standard deviation was 24, which is not fine, right? And so like that tells me that I've hit the right difficulty level overall, right? I've hit the right average difficulty level, but I have clustered them too tightly around that, and I need to spread out the difficulty, right? And so I need to basically find 2 questions and make them harder, and find 2 other questions and make them easier, and kind of use that as my new test. So when I'm adjusting a test, that's often what I'll do. So that all said, that was what this was here. I believe these were the actual data. This is actual data from my classes. So from a class I taught a while ago. So these were the scores on a test, right? They ranged from 100 down to 21, right? So pretty widespread scores here. So what we're going to do is we're going to find the sample standard deviation. Well, first we're going to write some hypotheses. Then we're going to find sample standard deviation and sample variance and see if it is different enough from my hypothesized variance for me to think that that the test was that the questions were clustered too tightly is what I'm trying to say here. So let's get a whiteboard going here. So I guess before I write any hypotheses, let's go back quickly to the question so I can see what we're looking at. So I'd like my exams to have a standard deviation of 10 points, right? That's the thing I'm going for here. Now, if you remember, variance is standard deviation squared. And so standard deviation of 10 points means variance of 100. And that's what we're actually going to do a test about. So my null hypothesis is going to be H null variance. So population variance squared is 100. This is, I don't know why this is not picking up these things very well. I think my hands might have some grease on them or something. That's messing with the electrical conductivity. Squared 100. There we go. And the alternative hypothesis is that it's not. Now I could reasonably say that I could reasonably do like a chi-squared is chi-squared. Sigma squared is greater than 100, right? I could do that. That's really all I'm concerned about. If you get a lower standard deviation or lower variance, I'm not that worried about that. It's also really uncommon. My variances are almost always higher than this. But let's go with this. So what I'm going to do is I'm going to go look at my data. It's right here, right? This is a test. This is one class's worth of test. And so I need to find the sample standard deviation there. And I'm absolutely not doing that by hand. I'm going to go do that in a calculator. And so the way we do that in a calculator, in case you have forgotten, where's my calculator? There it is we go to stat and edit and type it into a list. So that's what I'm going to do. I'm going to type all of these numbers. I don't know how many there are, but I'm going to type them all into L1 and then use one variable stats on L1. So you can, let me invite you to type yours in as well, just to get practice doing this. As I've said before, it really helps if you are doing something physical while you are learning, basically anything. There are different learning types, which a lot of people are familiar with. Audio learners, are visual learners, and kinesthetic learners. 21. And a lot of people falsely think, oh, well, I'm a visual learner. I should just do pictures for everything. And that's not true. What you should do is use every style for everything, because everyone, no matter what type of learning they prefer, learns best when they use more. So kinesthetic learners learn best when they are doing some sort of activity, including writing down or typing. That helps too. So just the act of typing this stuff in will help you remember it. It's kind of interesting. So let me recommend that you do that. So anyway, I've typed in my column. Let's make sure I've actually done this right. 59, 2, 41, 77, 172, 67, 72 again, 55, 21, 68, 100, 61, 77, 70. This looks like manufactured data. Maybe this wasn't real. You usually get a bunch of like scores that just coincidentally happen to be the same number, right? That look really suspicious, but that's actually what randomness looks like. This looks like I faked it. I don't remember if I did or not. So anyway, this is my data. So I'm gonna quit out of here, do one variable stats, stat cal variable stats, spell one, no frequency list. I hit that too fast. S was 17.87. So there we go. The standard deviation for this particular class was 17.87. So let's go write that down. I actually need sigma. I actually need S squared, don't I? So 17.8745 squared, 17.8745 squared. So my variance 319 point, we'll call it 5. So my S squared, about 319.5. And so what I'm going to do is my chi-square test statistic, chi-square, is S squared, or n minus 1 S squared over sigma squared. So it's actually degrees of freedom times S squared over sigma squared. So the sigma squared we're going to use is 100 here. It's the one from the null hypothesis. And the S squared that we're going to use is the one from our data. So that's what I'm going to do. 319.5 times, I don't remember how many there were. We'll go count in a second. Time divided by sigma squared. That's going to be my chi-square. All right, so let's go to the calculator. Did we have, yeah, we can just go stat edit. It'll count them for us, which is nice. We had 30. We had 30 data points. So n minus 1 is 29. So what I'm going to do is this. I'm going to do 29 times 319.5 minutes. This one right here, right? Times that divided by our hypothesized sigma squared, which was 100. Get this, 92.65. And you might ask yourself, is that number big? Right? Certainly seems huge compared to our other chi-square statistics, but let's think about what the mean was, right? The mean is equal to the degrees of freedom, which in this case was 29. So that is still pretty big, right? 92 is still large compared to 29. So this number does look large, but we are comparing it to a bigger number than we're used to. So yeah, let's put that on a graph and then see how significant it is. So this is chi-square 29, chi-square 29. We had 92 point something. So 29 is like right here, right? 29. And then this guy, not very well drawn to scale, was 92 point something, 92.65. 92.65. 0.65. Now, what we're going to do is notice that our alternative hypothesis was not equal to. So we're actually going to find this area and then double it. So I'm going to be looking at this area over here. And because not equal to is my alternative hypothesis is not equal to, I'm going to be looking at a corresponding area on the opposite side, or correspondingly sized area on the opposite side, right? So if we're thinking of this is a certain percentage of potential samples, then we want the same percentage of potential samples over here is the idea. So we're just going to double this number basically. So even though it's non-symmetric, we're still just multiplying by 2. So I'm going to do chi-square CDF of 92.65 up to infinity with 29 degrees of freedom. And we're going to multiply that number by 2. That'll be our p-value. Now, keep in mind that you're not always multiplying by 2. I'm only multiplying by 2 because it's not equal to, right? You would do a test to the right if it was greater than, test to the left if it was less than, just like any other hypothesis test. So, stat, no, not stat, I want distributions. Distributions, chi-square CDF, number 8. I'm going 92.65 up to some huge number with 29 degrees of freedom. So let's see what we get there. Tiny, it's times 10 to the negative 8. So when I multiply by 2 here, it's not going to matter. Yeah, still tiny. 2.8 times 10 to the negative 8. So my p-value is 0.000000028. So obviously smaller than our null hypothesis. That's going to make us want to reject the null hypothesis. Excuse me, always smaller. Obviously smaller than my 5%. So that's going to make us want to reject the null hypothesis in favor of the alternative. Make us think that my variance was not equal to 10 or equal to 100. So let's go to the whiteboard and write all that down. Whiteboard. All right, so this is, we get to chi-square CDF, 2 times chi-square CDF of 92.65 up to infinity with 29 degrees of freedom is about equal to 2.8 times 10 to the negative 8. You don't really need more decimal accuracy than that, right? Times 10 to the negative 8 pretty much is all we need to know, right? Anything times 10 to the negative 8 is going to be smaller than 5%. So it's less than 5%. So we are going to reject the null hypothesis, H naught. All right, so my conclusion looks something like this. This data suggests the standard deviation or variance. It was the question was written in terms of standard deviation. So I'm going to write my conclusion in terms of standard deviation as well. Sorry, let me move my picture out of the way here. Test is greater than 10. Well, different than. So we actually tested different than. So that's really what my conclusion should say, is different than 10. Now, certainly we can just glance at the data and notice that it's greater than. And so if, for instance, on a test, you wrote that it was greater than 10, I would 100% accept that, even though technically p-value for greater than would be 1.4 times 10 to the negative 8, but it's obvious from the data that that's the case, right? That greater than, the problem is that it's too big, not that it's too small. Yeah, that's it. That's chi-square test of a single variance. You're literally just testing a single variance against a hypothesized value. There is, I've got another one on the notes if you would like to try that. Right? Stephanie, the manager of a bank, thinks that customer wait times might be more consistent if she changes her line system. Notice that word consistent. Just 2 clicks there, consistent, suggesting that we are looking at standard deviation and or variance. And so you get all this data, right? And I will, I'll pause for a second and let you do it. Like you can pause the video and try this. So pausing. All right, now that you've paused the video and gone and done that, it turns out that this will give you, like, you should reject the null hypothesis if you do the test with this data. I don't remember what the numbers are, but you do end up rejecting the null hypothesis by a fair bit. And then that's A, is do the significance test, or do the hypothesis test, and B, I think that most my students usually disagree with me on this, and if you think about it for a second, you'll see why. So if you go to the bank and there's a 5-minute wait to get to a teller, it's fine. Stand in line for 5 minutes, no big deal. If you go to the bank and there's a 7-minute line to get to the teller, you stand in line for 7 minutes. No big deal. If you go to the bank and there's like a 20-minute line to get to the teller, that's gonna really annoy you, right? But a relatively small change in average wait time is probably not even noticeable. However, a relatively small change in variance of wait times is extremely noticeable. And the way you want to think about that is that variance of wait times is one person getting to the front of the line very quickly, and the next person not, right? The next person having to wait a long time, right? That's going to be super frustrating to a customer. If window opens up, person right in front of them immediately goes to the window, and then there's this long wait before they get to go to the next one, right? They're going to be super annoyed, right? If they see the person in front of them have a 1-minute wait and they end up with a 10-minute wait, they're going to be mad, or at least, I don't know about mad, but at least frustrated, right? So I would argue that variance and standard deviation are actually probably more important to the customer experience than average is. Anyway, that's a bit of a tangent there. So that's all the types of tests that we need for chi-square. Yeah, quick summary. I'll let you read through the summary of the notes yourself. I've just summarized all the tests here, how you write the hypotheses, how you do the tests, and how you find the test statistics. On an exam, if I ask for a test of a single variance, you will have to do this by hand. There's no like test of a single variance in your calculator, as far as I know. It might be hidden somewhere, but I don't think so. And I will also, if I ask for a goodness of fit test, I'll also ask for that one by hand for an entirely different reason. Although your calculator does have a goodness of fit test, if I ask for one on an exam, I'll ask you to do it by hand because not everybody has a goodness of fit test in their calculator. I don't know why they added it in later. And in fact, it's actually not that convenient to do the goodness of fit test in the calculator. I don't even remember how, but it's awkward. You have to calculate all the observeds and expecteds yourself, or excuse me, and all the expecteds yourself. It doesn't do that for you for some reason. I think you have to put it in as percentages. It's weird. It's very different than I would have expected. It's not at all like doing homogeneity. You don't use a matrix. And all you save yourself is like 1 line of typing in the calculator. It's probably 30 seconds faster to do a GeoF test than to just type it into the calculator. It's barely even noticeable, as opposed to independence and homogeneity, which are massively faster to do in your calculator. Like it's so tedious if you do it by hand, and so easy in the calculator. So anyway, I think that's all I want to say here. Make sure you know how to do all these tests. Oh, there is actually one thing I want to bring up, which is the hypothesis testing flowchart that I've been mentioning for a couple of weeks now. Stop sharing this. I'm going to go to, do I have it up? I kind of do. Let's go grab that. All right, so here's the module today. today's module. So let me share this up here. Yeah. So here is hypothesis testing flowchart, and you can get this in module. Here's the videos. You can see I haven't linked them yet, but I'll do that shortly. And here's the flowchart. And what you're going to find as we go a little bit further in the class is that the hardest thing is not doing the hypothesis test. From here on, you mostly just hit a couple buttons in your calculator and it gives you a p-value. Right? As long as you know which hypothesis test you're doing, it's usually pretty trivial, honestly, to do it. But figuring out which hypothesis test to do is not necessarily easy. As you can see, there are quite a few of these, right? So the ones that we've done so far, all the one sample stuff, one sample Z, one sample T, paired, or all the two sample, paired T, two sample Z, two sample T. And we've also done one prop Z, two prop Z, right? So we're really kind of starting to pile up a few tests here, right? All these guys and these guys and these guys. And now I'm adding on chi-square tests in which there's like 4 of them, right? These 3 plus this one over here, right? All of those things are chi-square tests. And then we're going to get a couple more. We're going to get ANOVA, and then we're going to get a 2-sample F test and a linear regression T test, right? And knowing which one to do in which situation gets very confusing after a while. So let me just strongly recommend that you start training yourself to think like this flowchart. This is the best way I've come up with in many years of teaching this, to help students choose which hypothesis test to do. Because generally speaking, if you're doing the right test, you're probably not going to have much difficulty. That's usually what I found is if the student can pick the test, they usually get everything right, or just about. And so you basically want to ask yourself 2 questions. What type of data do I have and how many samples? Right, that's really the essential question, right? Or not how many samples, but how many categories if your data is qualitative. So for number of samples, right? So quantitative data or qualitative data. Quantitative data, ask yourself how many samples, 1, 2, or 3 plus. We've covered 1 and 2, but have not done this one yet. That's next week. And then if you know it's once you know the number of samples, then you can ask yourself further questions. So from there, is your standard deviation known or not? Have you paired the data up, right? Depending on what kind of data you've got. If your data is qualitative, you basically want to ask yourself, how many categories do we have? Is this 2 categories? Just say yes, no questions, or is it 3 or more categories? So things like eye color, right? Blue, green, brown, dark brown. Blue, green, light brown, dark brown. Yeah. Or however else, so anything that has a lot of categories, right? So number of categories, if it has exactly 2 categories, so yes or no, then how many samples you got, 1 or 2. If it has more than, or if it has 3 or more categories, then you're doing a chi-square test, and it's really up to you to figure out which one after that. Goodness of fit, independence, or homogeneity. So you want to get yourself thinking about this, thinking like this when you're trying to decide which hypothesis test to do, because on an exam, what's going to happen is I'm just going to give you a statement like, here's this problem I want you to answer. And then the first part of the question will always be, what test should you do and why? Right? And an answer I'm looking for there is like, I have qualitative data and there are 2 samples, so I'm doing a 2 prop Z test, something like that. And so you want to get good at this. You want to understand that or remember the flowchart. And to help you practice that, I have made this version, which is the same thing, but everything's blank. So you can try and fill in, you can ask yourself, okay, if I'm doing a quantitative test and I've got paired data, what should I do? And you should know it's a paired t-test. What if I know sigma and I've got 2 samples where I don't know sigma, or where the data is not paired and I don't know sigma, right? What should I do here? Well, 2 sample t, right? So you want to basically be able to fill in all of this stuff down here. Now, that said, we haven't actually covered everything on this table yet, but most of them, right? We've got all these chi-squareds, and then this one, which is this is the test of a single variance. And then after that, where you should go from there is not even have this, just have a blank piece of paper where you have to write, where you have to figure out, okay, what question do I ask myself first? Ask myself data type first. What question do I ask about that? If my data is quantitative, then what do I ask? You should need to know, ask myself number of samples, 1, 2, or 3 or more. Or if my data is qualitative, what do I need to ask? How many categories? 2 categories or 3 or more categories, right? And so basically, once you can recreate this chart, not from memory, but by thinking about it, then you don't need the chart anymore, right? Then you've transcended the chart at that point. And that's the point you want to get to. If you can get to there, I find it hard to believe that you would get anything but an A in my class, or at least an A on the third test. So yeah, that's really, really helpful. So go through those stages of think about, look at where everything is. Don't try to memorize it. Instead, try to think like the flow chart. And once you can do that well enough to fill this in pretty confidently, then don't even start with the chart. Just have a blank piece of paper, and you have to remember the questions, and then also remember which tests go where. Once you can do that, you'll be set. Okay, that is, I think, all I wanted to say there. Let's stop sharing this. Yeah, I believe that's all I want to say. So I'm going to go ahead and stop the recording now, and I will see you in the next video, which is going to be about ANOVA, analysis of variance, which is an interesting topic, but that's next week. I'll see you then.